Hello everyone, my name is Davor Valdez and this is my presentation on synthesis, characterization, and analysis of lithium zirconate. The purpose of this presentation is to demonstrate the different applications of material science throughout this research project, explain the steps to synthesize lithium zirconate, navigate how to characterize the synthesized zirconate, and illustrate why this project can be useful. So what is lithium zirconate? Lithium zirconate is a white crystalline powder classified as a Caswell silveride. It is made of lithium, zirconium, and oxygen generally packed in monoclinic unit cells, although it can also exist in tetragonal unit cell form or orthorhombic unit cell form, depending on the ratio between lithium, zirconium, and oxygen. Lithium zirconate is a semiconductor, meaning that if enough energy is applied to the powder, its valence electrons can jump from the valence band or highest occupied molecular orbital to the conduction band or lowest unoccupied molecular orbital. When this happens, the zirconate begins conducting and as a result pushes chemical reactions to occur the same way a catalyst does. For the synthesis of lithium zirconate, the Bikini method was used. This method uses the transesterification of citric acid and ethylene glycol to evenly distribute metal cations to make relatively pure and even powdered crystals. The materials used for this were lithium nitrate, zirconium oxynitrate hydrate, citric acid, ethylene glycol, and distilled water. The equipment used was a steering and heating plate, an induction oven, an oil heating vat, a ceramic crucible, and a glass beaker. And the steps for the synthesis were the polymerization, calcination, and annealing. To start with the polymerization step, citric acid, lithium nitrate, and zirconium oxynitrate were dissolved in distilled water and stirred at 90 degrees Celsius for 2 hours. After that, ethylene glycol was added to the solution to polymerize it and become a gel. This solution was left to polymerize for 7 hours at constant stirring, often checking whether more water needed to be added. In terms of reaction mechanism, once citric acid and the metal salts are added to the water, the salts begin dissociating into their conforming ions as shown in steps 1 and 2. Subsequently, the metal cations form coordinal bonds with the carboxyl groups of citric acid as depicted in steps 3 and 4. During the 2 hours, most of these ions bond with citric acid molecules until ethylene glycol is added. Once this happens, a polymerization reaction begins as presented in step 5. These polymeric strands are left to grow for 7 hours until the solution becomes a gel. Once the 7 hours passed, the solution was taken out of the oil bath and left to rest for a couple minutes. Once the polymerization step was finished, the gel was transferred into a crucible and put in an induction oven to calcinate. The oven was set to raise the temperature inside at a rate of 10 degrees Celsius per minute until 450 degrees Celsius were reached. After that, the high temperature was maintained for 2 hours to allow for all organic and volatile compounds present in the gel to pyrolyze and for the water to evaporate. This process causes the gel to boil up and slowly dry into a blackish solid foam, mainly containing an even mixture of lithium and zirconium carbonates. Due to the low reactivity of the chemicals used, this step was conducted under normal air. To finalize the synthesis of lithium zirconate, the charred foam from the calcination step was first grinded down using a pestle. The crucible was then put back into the oven at the same heating rate as the calcination step. This time, however, the oven was set to reach 950 degrees Celsius. At this temperature, carbon evaporates in the form of gaseous carbon oxides and other carbides. At the same time, the high temperature allows for oxygen to oxidize both the zirconium and the lithium present in the foam, generating the lithium zirconate crystal powder. For the reaction to come to completion, annealing was left to occur for 12 hours. After this, the crucible was taken out of the oven and in it there was a white lithium zirconate powder left. Once synthesis was finished, it was necessary to check that the resulting powder was in fact lithium zirconate. For this, X-ray diffraction was used on the powder. The equipment necessary for this was a Bruker X-ray diffractometer, a Bruker specimen holder, and a Windows computer. Additionally, the software used for this was Expert HiScore Plus, and the steps done were X-ray diffraction and results and data analysis. Started with characterization, X-ray diffraction of the powder was taken. For this, the diffractometer was set to take measurements at an angle ranged from theta equals 10 degrees to theta equals 40 degrees. First, about 1 gram of the powder was put into a 32 millimeter specimen holder. Then, the holder was placed into a spring lock and into the diffractometer. After that, a knife edge was placed around 2 millimeters away from the surface of the powder to have a clearer peaks in the data, and the process was started, taking about 30 minutes to complete. Once the process was finished, raw XRD data was obtained, with each peak representing a specific crystal structure within the powder. This raw data was then put into the software expert HiScore Plus. In it, the analysis of the data was conducted. First, the peaks of the data were searched using the program. As we know, different compounds and crystalline structures will have different peaks at different angle positions, meaning that the way to confirm whether the powder is lithium zirconate or not using XRD, the peaks of the data have to be matched to an existing reference. To find a match, Expert HiScore was connected to the Crystallography Open Database, a bank of data files for more than 500,000 different reference patterns for thousands of different chemicals. Then, patterns containing lithium, zirconium, and oxygen, excluding every other atom, were searched, outputting 5 peak patterns presented in the picture, starting from the second row downwards. After that, the pattern with the highest similarity was picked, and because the peaks were virtually the same, it could be confirmed that the synthesized powder was in fact lithium zirconate. Expert HiScore can give unit cell information of the reference pattern, which can be used to make further calculations for unit cell volume and parameters, but these calculations were not pertinent for this research project. As explained earlier, lithium zirconate can be used as a catalyst due to its semiconductor properties. Because of this, the next steps on this project are to test its photocatalytic properties first by reducing organic dyes. Once that is tested, further testing can be done on its efficiency at different conditions such as temperature and at reducing different contaminants such as carbon dioxide at the atmosphere and microplastics in water. Once these tests are finished, they will show whether lithium zirconate is a compound worth using in industrial settings or waste treatments, in addition to showing that material science is an innovative area of study and that is fundamental for advancing technology. Thank you for your attention.